so let's wait for the recording to start, then we'll begin. Okay, 3.1, electrical conduction. So basically in this chapter, it's being divided into two main subtopics. The first one is all about electric current. It tells you what happens in the electric current, how electric current is being generated, how it moves, and so on. And then the second thing is a direct current circuit, where we're going to look at all the connections, the series parallel circuit, the circuit with 1 loops and 2 loops, and how to simplify the circuit. That will be the second part in the chapter 3. So today we're going to focus on the first part, which is electric current. We're going to see what is the things that affect electric currents, how to calculate the numbers of charge in the currents, and so on. So 3.1, use electric current. That is a learning outcome. So first of all, we have equations I equals to dq over dt. We have seen these equations in lecture, and we have learned how it works. Whenever there is a charge moving in the circuit, then I will be generated. Okay, I will be generated. So if they are not moving, means there's no current. But if the electron is start to move in the current, in the circuit, then it will give you current. Therefore, you have equations I equals to dq over dt. You look at how fast it moves. The faster it moves, the larger the I. And then one thing that you have to take note is the equations. We have the variables. We have the quantity known as Q. Now, what is Q? Q, it represents charge. But there is a misconception among students, where students always thought that charge represents electron. Okay, no, it actually represents the total electrons in the current, not just 1 electron or 2 electrons, but it is a lot, it is plenty, okay, more than that. So you're not just looking at what happens to one charge, you're looking at what happens, how fast the charge, all of the electron in the circuit moving. Therefore, Q can be calculated by using NE, where N represents the numbers of electron, okay, numbers of electron, and then E here, once again, it is our elementary charge. Okay, if you look at the list of constant, it is elementary charge, but when in chapter 3, this elementary charge, it also represents our electron. Right? So when you look at the list of constant, if you're going to search for the values of E, you search for the values for elementary charge. Okay, and elementary charge, we got proton and electron. In this case, in this chapter, we are going to focus more on electron. So you look at how many electrons, okay, how many electrons do you have in the circuit? In the circuit. Therefore, you calculate current by using dq over dt, not just 1 electron. Okay, don't use the values for 1 electron. You have more than that. Okay, so you might not that clear between Q and E yet. Let us go through example 1 and see what is the main difference between Q and E. A silver wire, it carries a current of 3 ampere. So you are given I here. So given charge of electron, E is equals to 1.6 times 10 to the power of negative 19. So this question is being very nice to you. It tells you the charge for 1 electron. You don't have to search from the list of constant. So you have E is equals to 1.6 times 10 to the power of negative 19. Determines the numbers of electrons per second. Aha. So if you look at these questions, okay, question is asking for numbers of electron, but not just N, but it is per second. Okay, not just N. It comes with per second. So it actually asking for N per T. Okay, N over T, numbers of electron per second. So not just numbers of electron, not just time, but it is asking for a fractional value, which is N over T. So numbers of electron passes through the wire. So now what you want to do, you want to see how many electrons you have in the wire. Okay, you need the value. But then, do we have enough information? Let us begin with equation for I. So I is equals to dq over dt. In our calculations, we can actually just write it as q over t. If you look at just these equations, you don't have enough value. You don't have any information about q. Okay? But again, if you look at these equations, you also don't have n. Question is asking for n. Okay? But you don't have n in your equations. And if you look at these equations, you don't have enough information to calculate q. Therefore, what you can do is by substituting q equals to ne into the equations so that you can have n in your original equations. So now let's see. If you plug it into the equations, you're going to obtain I is equals to ne over t. Aha! So now you have n over t in your equation. Okay, you have n over t in the equations. Meaning that now you do have enough information for you to calculate the value. You do have the right equations for you to determine n over t. So rearrange the equations. N over t is then equals to I divided by E. Wait, yeah, should be. Oh yes. Okay, I divided by E. So I over E. Okay, I over E. So you plug the value into the equations. You have 3 divided by 1.60 times 10 to the power of negative 19. Therefore, it is equals to 1.88 times 10 to the power of 19. Now, what is the unit for n? Okay, this is very important. What is the unit for n? So n, it depends on the question. In this question, it asks you to calculate the numbers of electrons. Therefore, the n in this question, the unit it represents, okay, the unit that you use in a solution is electrons. If the question asks you to calculate the numbers of proton, then the unit for n is proton. Okay, if the question asks you to calculate, for example, numbers of particles, then the unit for n is particles. Right? So if the questions, for example, ask you to calculate the numbers of a table in a class, then n will have a unit tables. All right? So in this case, since the question asks you to calculate the numbers of electron, therefore the unit for n is electron. Okay, the unit for n is electrons. And then per second. Okay, so per second. Because it's n over t. Just that you have to be extra careful. This n, the unit, you don't have a fixed unit. It depends on the question. If question asks you to calculate numbers of alpha particles, then the unit in your final answer should be alpha particles. Questions ask you to calculate electron, so the unit in your final answer is electrons. Okay, it's electrons. So it depends on the questions. You cannot simply give it any unit, and you cannot leave it blank. This is a very common sin mistake in the final exam, where students, they always leave it blank. They thought n, it doesn't have any unit. Actually, it do. Okay, it do have unit. In this case, we have electron, proton, particles. It depends on the questions. All right. So that is your questions A. Okay, questions A. Just be extra careful with n. And then the questions B, the amounts of charge flow through the cross-sectional area. Aha. Now this question is asking for the amounts of charge, total charge. Total charge means the question is asking for Q. Okay, it is asking for Q. It is not asking for E. E is the charge of electron. If you look at the question, charge of electron is E. Amounts of charge or total charge is Q. So that is the difference. All right, that is the difference. So the amount of charge flow through the cross-sectional area of a wire in 55 seconds. Okay, in 55 seconds. So how are we going to solve it? Can we calculate Q by using NE? Obviously cannot, because we don't have the numbers of particles. Then can we calculate it by using I and T? Well, I think yes, we do. Why? Because we do have I from the main questions, and we are given the time in the questions B. So let's try. I equals to Q over T. Rearrange the equations. Q equals to IT. Given I is 3 and given T is 55. And yes, we do have enough informations. Therefore, Q is equals to 165 and the unit is coulomb. 165 coulomb. So then that is questions B. Okay, so take notes the difference between E and Q. What is the difference between E and what is Q? And then what is the numbers of electron? What is the unit that you should use for N? So N, it depends on the questions. Remember, keep that in your mind. It's very, very important. Because not just this topic, but you're going to use N very often in chapter 11. Okay, chapter 11 is all about particles. So you have to know what unit to be used in chapter 11 for N. Okay, so it depends on the questions. Okay, it depends on the questions. So it could be electron, protons, particles, or any other things. Okay, as long as it's being mentioned in the questions. So now I give you 2 minutes to write it down before I proceed to example 2.
Madam buka voice tak?
All right, now let's look at the example 2. Okay, so 3.1, we got 2 questions, example 1 and example 2. Example 2, a current in the bulb is 2 ampere. So again, you are given the current, I equals to 2 ampere. What is the charge that flows through the bulb in 5 minutes? So given times t equals to 5 minutes, but this is not in SI unit, you need to change it into second, right? Second is SI unit. So what is the charge that flow through the bulb? So what does it mean? Actually, it refers to total charge, the Q, not electron, right? Not E, but Q. So what is the charge that flows through the bulb? So given I and T, and you want to determine the values of Q. So Q equals to IT.
IT.
Equals to 2, and then time, remember to change it into second. So it should be 5 times 60.
60.
So it is equals to 600 coulomb. Okay, good. Okay, good. So that is our questions A. Now, questions B, it asks you how many electrons flow through the bulb. Now it's asking for how many electrons. How many electrons? So it is asking for N It wants to know the quantity of electron that flow through the belt. Again, in 5 minutes. So this 5 minutes is very important. If it is not in 5 minutes, then you have to recalculate Q. But now, because it mentions 5 minutes, and from previous questions, we have Q for 5 minutes. Therefore, we can still use the Q from questions A. So Q equals to NE. Okay, Q from questions A is 600 equals to N. So E, if you refer to the list of constant, you will have 1.6 times 10 to the power of negative 19. So the numbers of electron flowing through the belt in 5 minutes is equals to 3.75 times 10 to the power of
21.
Good. 21. And what is the unit now?
Electron.
Very good.
Electrons.
Okay, so the unit is electrons now, because the question is asking for how many electrons. So electron is our unit in questions B. So what I wanted to do, I wanted to add in one more question. Okay, so how many electron? Okay, question C. How many electrons flow through the belt in 1 minute? So if you have a question where the time given is not same as question A, then you have to recalculate Q. Okay, you have to recalculate Q. So when it comes to question C, okay, you need to recalculate Q by using IT again, which is equals to 2 times 1 times 60 seconds. So it is equals to 120 coulomb. So total charge flowing through the belt in 1 minute is 120 coulomb. So from here, you can then calculate the numbers of electron. Okay, so I'll leave it to you. You calculate and see what is the answer. So I wanted to add in one additional question so that you can see the difference between questions B and question C. So if it is 5 minutes, then you can use the Q from previous question. But if the question changed the times in the questions, then you need to recalculate Q. You can no longer use a Q from questions A because now the times is not the same, right? So I give you 3 minutes to write it down. Okay, you add one more questions in your books, and also you do the solutions. Okay, you show the solution so that you can see the main difference. The main difference is in terms of total charge, right? So 3 minutes from now for you to write it down. All right. So done. We are done for 3.1. But 3.1, other than the calculations type question, there's one more type of questions that you need to take notes, which is sketching. Okay, sketching type questions. So when it comes to chapter 3.1, wait, yeah, here. Okay, sometimes questions like to ask you how electron flows in the free metals, or what happens when you switch on or before you switch on the power supply, before electric field is being applied across the conductor. Then you have to know how to sketch these two diagrams. The first diagram is before you open the switch, before you connect it to the power supply, before you apply the electric field across it. Okay, and you have to show the zigzag motion. And after you apply the electric field, then you need to know how to sketch this one. The directions of electron flow, the path of electron flow. So you need to know how to sketch these two diagrams. It's quite a popular questions in the past year exam, in the past exam, right? So you need to know how it moves, the shape, okay, the zigzag shape before you got a power supply, the linear shape before you apply an electric field over it, across it, and then the directions of electric field, the directions of electron motions, electron move, the directions of current. All those directions you need to know because you need to put it in your diagram, right? So other than calculations type question, this is one very popular questions in the past exam. Not graph sketching, sorry, diagram sketching. Okay, you need to sketch the diagram. You need to explain a bit how it moves. Before, it moved freely and randomly, and then after, it moved opposing to the electric field, and then opposing to what, like some more, opposing to the directions of current, and so on. All right, so this one I'll leave it to you. You go through it again and see what happens to the F, E, I, V, okay, all these terms, the directions of motions especially. All right, now let us go back to the questions. So we are done with 3.1, two calculations type questions, and then the diagram, okay, the sketching questions. Let's look at 3.2. 3.2, we have Ohm's law and resistivity. Okay, Ohm's law and resistivity. Now, what is Ohm's law? Again, Ohm's law, it tells you the relationship between V and I. Okay, where your V is directly proportional to I if, this is a very important condition, if or when temperature is constant. If temperature is not constant, then V is not proportional to I. Okay, it's not proportional to I. Therefore, when you change it into mathematical equations, we have V equals to IR. So we are going to use these equations very often in this chapter. And then after that, we look at what is the things that will affect the values of resistance. You cannot say change V will change R. You cannot say R is being affected by I. Why? Because of this relationship. I depends on V and V depends on I. That's it. R is actually acting as a constant in this equation. So R is fixed as long as you're using the same resistor, as long as you didn't modify it, you are keeping it the same physical structure. Okay, now how are we going to change the values of R then? In this equation, it's a constant, but sometimes we want to modify it, we want to change the values of resistor. So what should we do? We look at R depends on what? First thing, R depends on the length of the conductor, of the wire. So obviously, if it has to travel further, then it will experience more opposing force. Okay, more repulsive force, or we call resistance, if it wants to travel further. And then R is inversely proportional to area. Well, again, it makes sense. If you're walking on a path, on a road that has a larger surface, of course, you will experience lesser resistance. Okay, you will experience less resistance compared to you're walking on a small surface area. Okay, on a path that has a small surface area. So R is proportional to L and R is inversely proportional to A. When you combine them together, R is proportional to L over A, and then we want to change it into mathematical equations. Therefore, it becomes R equals to rho L over A, where rho is resistivity, and this resistivity It depends on, it depends on two things. It depends on the material of the conductor, materials of the wire, and also the temperature. And also the temperature. So rho, it depends on these two things only. If you're looking at something that happening at the same temperature, then the resistivity is always fixed, always constant. So R equals to rho L over A. When you rearrange the equations, then you're going to obtain the equations given in your learning outcome. Resistivity is equals to RA over L. Basically, you just rearrange the equations from R, from the equations for R. So we have two equations in this subtopic. We focus on the Ohm's law, and then we look at what is the things that affect the values of resistance. How are we going to change the value? Which is by changing its physical structure. So example 3, when a potential difference V equals to 240 volt is applied across a wire that is 200 cm. Again, this is not SI unit. You need to change it into SI unit. So this is a length across a wire that is a 2 meter long. The current per unit area, not just current, you look at the whole statement, current per unit area, meaning that this one is actually your I over A. So given I over A is equals to 7.14 times 10 to the power of 9 AM squared. So calculate the resistivity of the wire. So let us start from the resistivity equations. Rho equals to RA over L. But if you look at these equations, we don't have R. R is an unknown. And again, we don't have the A. We don't have any information about A. What we have is just the L, where L is equals to 2 meter. So what should we do now? If you look at the equations again, you are given the V. You are given V, and then you look at the equations, you are given a value I over A. You have V, you have I, and both of them, they are related to R. So let's see how are we going to change it. So V equals to IR. If you rearrange the equations, R is equals to V over I. So let's sub V over I into our equations. We will then obtain rho equals to V over I times A over L. Now let's see. Now we have L, and then we have V. But then we don't have A over I. What we do have is I over A. So what should we do? We flip it over. So I over A, now we flip it over to becomes A over I, meaning that the value right here will becomes 1 over 7.14 times 10 to the power of 9 AM squared. AM squared. So you plug this value into the equations, you will then obtain, let's see, V is 240, and then divided by A over L is 1 over 7.4. So this one is a 7.14 times 10 to the power of 9, and then L given 2 meter. Therefore, resistivity is equals to 1.68 times 10 to the power of negative 8 ohm meter. So this is your final answer. This is your final answer. So that is how you solve it. You solve it step by step. You try to start from the equations of for resistivity. So why? Because question tells you to ask you to calculate resistivity. So always start from equation for resistivity. That is the trick. That is how we say technique in solving questions. So I give you 2 minutes to write it down. If you have any questions, you may ask, including the summary and also the solutions for example 3. So 2 minutes for you to write it down. Then we'll proceed to example 4. If you are done, you may try example 4. Example 4 is a questions without value. So how are you going to solve this type of questions? right, now let's look at example 4. See how to solve the questions without any value. So example 4. Oops. Okay. Now you have two wires P and Q with a circular cross-sectional area. Now this circular cross-sectional area, actually it wants to tell you now you have a circular shape A. Okay, the surface area is a circle. So you're going to use the equations A equals to pi r squared if you want to calculate the surface area, or pi d squared over 4. All right. So they are made of the same metal. Aha. Why the term same metal is very important? Now, even though you have two different wire P and Q, but if both of them, they are made up of the same material, same types of metal, it means they will have the same rho. Okay? Same metals, it gives you the hidden informations where rho for P and rho for Q, they are equal. And then they have equal length. Okay, another information given is they have equal length. If the resistance of wire P is 3 times greater, so resistance of wire P is 3 times greater than the resistance of wire Q. This is the key part in solving example 4. Determines the ratio of their diameter. So now let us see how are we going to solve these type of questions. Well, we have A. We don't have A, sorry, but we do know the shape. Okay, we do know the shape of an area, and now we have rho. We have informations about the length, and then we have informations about the R. Questions asking for diameter. Well, since how are we going to solve it then? It's about the physical structure of the resistor, right? Therefore, now let us make a table. Okay, let us put every piece of information into the table first. So now we have a wire P, wire Q, and then this column we leave it for the relationship. Relationship of what? Relationship of P and Q. And then here is the variable. Let us start from rho. So two wires P and Q, they are made of the same metal. So first information is about rho. What do we know about rho? So for P, we have rho P. For Q, we have rho Q. What is their relationship? Now, because of the term same metal, we know that rho P is equals to rho Q. Therefore, we can simplify the both of them as rho. Okay, as rho. So first information we have is about the resistivity. The second piece of information given is now they have equal length. So length for P, I'm going to call it LP. Length for Q, I'm going to call it LQ. What is their relationship? According to the questions, they are equal. Once again, LP equals to LQ. I'm going to simplify it and write it as just L. And then question tells us about the resistance. Okay, it tells us about the resistance. So we have R. R for P, of course, I'm going to call it RP. R for Q, I'm going to call it RQ. What is their relationship? Resistance of wire P is 3 times greater than wire Q. So P is larger than Q. Larger by how many times? Greater is 3 times. Okay, 3 times greater than Q. So the relationship is RP is 3 times of your RQ. So RP equals to 3RQ. And then what else? Okay, we want to determine the ratio of the diameter. Okay, let's see. Ratio of diameter, what does it mean? It means now we have D in our equation. We should have D in our equations. And then D for P, D for Q. Okay, their relationship, what we do know is that dP is not equal to dQ. And now we want to find the ratio. So what is the ratio? So let us begin with, okay, now if you look at the relationship, you should be able to tell where should we start. Okay, so first one, it just gives you the relationship between rho. The second one, it just gives you the relationship between L. But the third one, it gives you a proper mathematical equations where you have Rp equals to 3RQ. So let us start from this equation. Okay, let us start from this equation. So Rp equals to 3RQ. If you look at the table, we are talking about the physical structure of the resistor. So Rp, I'm going to expand it and use the equations rho L over A. Okay, rho L over A. Now, if you want to use rho L over A, then make sure to add a subscript. So rho P LP AP equals to 3 times rho Q LQ and then AQ. But if you look at the equations, okay, if you look at the equations, A, well, we don't have any information about the A. But what we do know is now we have a circular cross-sectional area, right? Let us go back to the main question. We have circular cross-sectional area, meaning that our A is now equals to pi d squared over 4. So we can expand these equations and we can also simplify it at the same time by removing this subscript. Why? Because according to the relationship table, the relation in the table, we have rho P equals to rho Q, we have LP equals to LQ. So let us simplify it. So what I have now is rho L over A is pi D for P, okay, pi D squared over 4 equals to 3, and then rho L over pi dq squared over 4. This is the equations after I simplify it and expand it according to the information that we have. Next step, well, now I want to simplify it even more. How? Let's look at the equations. I have rho on both sides, so I can cancel it out. I have L on both sides, I can cancel it out. Okay, and then pause. I'm going to stop right here and rewrite the equation. Okay, so I do it step by step. Saya tak rushing, nampak tak? Saya buat slowly. Saya tak kejar jawapan up here. Saya buat step by step. So now what am I going to do? After I cancel it out, it becomes 1. So now it's 1 over this whole thing. I'm going to flip it over. It becomes 4 over 4 pi. Oh, sorry. 4 over pi dp. Okay, pi dp squared. And then here it is equals to 3, well, 4 over pi dq squared. So now, when you have equations in this form, you can simplify it furthermore. How? Let's see. I have 4 on both sides, so I'm going to cancel it out. I have pi on both sides, I'm going to cancel it out. Okay, I'm going to cancel it out. So what I have right now, I have 1 over dp squared equals to 3, okay, 3 over dq squared. I'm going to rearrange it. Okay, I'm going to put all unknown together. Why? Because questions is asking for ratio. So dq squared over dp squared equals to 3. Okay, so rearrange the equations. We have dq over dp equal to square root 3. So that is your final answer. That is the ratio. Okay, ratio of q to p. So since the question is just asking for ratio, it doesn't tell you whether it wants it from P to Q or Q to P. Then it is up to you whether you want to write it dQ over dP or dP over dQ. If you got final answer dP over dQ, then it should be written as, okay, it should be written as dP over dQ equals to 1 over sub 3. All right, 1 over sub 3. That is the ratio. So you can use either one. It depends on how you rearrange your equations. Okay, it depends on how you rearrange your equations. So I give you 3 minutes to write it down. This question is slightly more complicated. So I give you 3 minutes to write it down before we proceed to next subtopic. Okay, so now let us move on to the next subtopic. Subtopic 3.3, variations of resistance with temperature. So just now we say when it comes to a Ohm's law, we assume temperature is constant. What if temperature is not constant? So if temperature is not constant, then this is the equations that you have to use. Why? Because if you look at the equation, there's a part that shows you there is a change in temperature. So R equals to R naught bracket plus alpha T minus T naught. Now alpha is the value that we record at 20 degrees C. 20 degrees C is our reference temperature. Okay, so if you look at all your electrical instruments, your electrical items, if you have a values alpha written on the box, then that alpha is actually being recorded at the temperature 20 degrees C. Okay, so that is our reference temperature. So sometimes questions might just ask you, okay, now you calculate the alpha in the questions, but then questions didn't give you initial temperature. It just gives you the final temperature. Then you yourself have to know alpha it's being recorded at 20 degrees C. Okay, for example, questions number 6. Okay, we'll talk about that later on. So what you have to know, 20 degrees C, this is our reference temperature. So R equals to R naught 1 plus alpha T minus T naught. Okay, this is for you. This equation is for you to calculate R final. Okay, this is for you to calculate R final. So when to use these equations, actually it's very simple. This is the only equations with temperature in chapter 3. So if you look at the questions mention there's anything about temperature, the change in temperature or whatsoever. If you are given the temperature, then this is the equations that you should use. Okay, so that is a trick. I would call that as a trick. Okay, how to determine which equations to use. If you are given temperature, then most likely you need to apply this equation, most likely. Example 5. A copper wire has a resistance of 25 milliohm. This is your R at temperature 20 degrees C. Okay, this is T. Now, usually 20 degrees C, we'll say it, we'll treat it as a T naught. R is a R naught. Okay, this is the initial statement, so initial value. When the wire is carrying the current, heat produced by the current, because of what? Heat is being produced because of the collisions of atoms and electrons inside the wire. All right, so heat produced by the current causes the temperature of the wire. Now look at the statement. Increase by 27 degrees. This is not your final temperature. Okay, this is not T final, but rather it is your T. Okay, it is your delta T, the change in temperature. So delta T is actually equals to T minus T naught. So straight away, it gives you the values for this part of the equations already. Okay, T minus T naught. So given temperature coefficients of resistivity, this is alpha for copper is 6.8 times 10 to the power of negative 3. Calculate the change in wire resistance. So what the questions want is delta R, but not R. So how are we going to transform the original equations into delta R equations? So let us begin with the equations. R minus R equals to R naught bracket 1 plus alpha T minus T naught. I'm going to multiply it into the bracket. So I have R equals to R naught. Yeah. Okay. R equals to R naught plus alpha R naught or R naught alpha. Okay, R naught alpha. It's up to you how you want to arrange it. Okay, I just want you to see I have R naught on both sides. So R naught plus R naught alpha now. T minus T naught is delta T. Okay, T minus T naught is delta T. So R naught plus alpha, R naught delta T. Rearrange the equations. I have R minus R naught equals to R naught alpha delta T. If you look at the equations again, now I have R minus R naught, which means I can then simplify the equation as delta R. Delta R is equals to R naught alpha delta T. So now I have delta R already, and that is the change in resistance. So once I have the equations, I just need to plug in the value. So given R naught is 25 times 10 to the power of negative 3, alpha given 6.8 times 10 to the power of negative 3, delta T given 27 degrees C. Now, when it comes to delta T, you can use either degree C or Kelvin. It doesn't matter. Reasons I've already told you last semester. All right. But if you're just looking at temperature, then you need to use temperature in Kelvin. But in this question, it doesn't matter. Why? Because T minus T naught is equals to delta T. It's the change in temperature. So it doesn't matter whether you change it into Kelvin or not. You can use degree C or Kelvin in these equations. Okay, in this equation. Sebab dia guna relationship tolak. Okay, kalau tolak, dia tak kisah. Because terlepas tolak, this part is always delta T. So when it comes to delta T, it doesn't matter whether you're using degree C or Kelvin, right? So plug in the equations, and then eventually you will obtain delta R equals to 4.59 times 10 to the power of negative 3 ohm. All right, so that is your final answer for questions A. Questions B, if initial current or original current, which is your I naught, is 10 milliampere, and the potential difference across the wire remain constant, what does it mean? It simply means V final equals to V initial. What is the final current? So this one is unknown. Now you want to find I naught n. You have an I naught, you want to find I. You know the relationship between V and V naught. How are we going to calculate I naught? And how are we going to calculate I? Based on all these informations given. Let us begin with the equations R. R equals to R naught, 1 plus alpha T minus T naught. This is the general equations. If you look at this question is about change in temperature. So how are we going to link current with this equation? So you look at the relationship between I, V, and R. So V equals to IR. Rearrange the equations. R equals to V over I. Okay, R equals to V over I. So if you are looking at initial R, okay, R naught, then you use V over I naught. Now the reasons why I just use V right here is because question tells us V remain constant. Okay, otherwise you need to add a naught right here to indicate that that is the initial potential. Okay, initial potential difference. But now it tells you potential difference remain constant. That's why when you change R, when R changes, I changes. Okay, when you have an equations, only two variables can change at one time. So now in this case, you have V remain constant. Therefore, when R changes, I also changes. So plug it into the equations. V over I equals to V over I naught, bracket 1 plus alpha delta T. So you plug in the equations, you plug in the value, eventually you should obtain I final equals to 8.45 times 10 to the power of negative 3 ampere. Okay, so V and V cancel out, yang lain kamu masukkan nilai. So when you have equations, V equals to IR, okay, kalau kamu ubah R, bermaksud salah satu V atau I akan berubah. Terpulang pada kamu punya soalan. Okay, terpulang pada kamu punya soalan. Dia punya idea actually sangat lebih kurang, kita kata lebih kurang sama dengan chapter 2. Chapter 2 ya C equals to Q over V. Kalau C constant, kamu ubah Q, V ubah. V ubah V, Q ubah. Case ini, kalau R constant, R bertindak sebagai constant, kamu tak ubah dia punya physical structure, okay, maka V dan I dia proportional to each other. Tetapi, once Anda modify resistance atau capacitance, dan situasi dia akan berubah. Kalau kamu modify resistance, okay, bermaksud V dan I salah satu sahaja akan berubah. Lagi satu, kamu akan kekalkan dia sebagai nilai constant. Okay, kamu akan kekal dia sebagai nilai constant. Sebab kamu tak boleh ubah semua benda serentak. Nanti akan pening. So sama juga when it comes to equation C equals to QV, kalau anda ubah capacitance, cuma Q atau V sahaja boleh ubah. Macam mana kamu tahu yang mana satu ubah? Kamu tengok whether battery is connected or disconnected. That is a trick. Okay, kita kata itu adalah trick. So salah satu mesti constant. So when it is constant means that you can actually remove it from your equation. Right? So kerap kali kalau dia bagi kamu maklumat yang ada berkenaan dengan nilai constant sebelum dan selepas kamu buat sesuatu perubahan, biasanya dia nak kamu remove that from your equation. You can cancel it out. Normally, it's like that. Okay, normally it's like that. Alright, now I give you 3 minutes to write it down before we proceed to example 6. Okay, this question is a bit long, so I give you 3 minutes to write it down.
Madam,
Yes?
yang apa tu tadi, yang V tu kita potong kan? So jadi
Ya,
satu
V
kan?
memang boleh potong. Ya, jadi 1.
Sekejap.
So dia menjadi 1 over I and then sama dengan 1 over I naught. But I naught is 10 milliampere. Jangan tercicir milli dia.
Sebab saya dapat 8448.
Oh, 848 tak ada masalah.
8.45 darab 10 kuasa 3.
Kalau 8.48 ada 4845 dia beza sikit tak ada masalah.
Medan dapat negatif 3, saya dapat kuasa 3.
Oh, kamu dapat positif 3.
Tengok salah mana.
Yang lain dapat berapa? Positif ke negatif? Yang lain cuba kira dan bagi tahu saya, kamu dapat positif atau negatif? Yang lain tak kira loh. Okay, we'll wait until got the next answer before we proceed to example 6.
Madam,
Yap.
saya dapat negatif 3.
Kamu dapat negatif 3. So mesti ada salah seorang yang salah key in calculator. Okay, so see. So when you plug it in, you should obtain 1 over I equals to 1 over 10 times 10 to the power of negative 3. Bracket. And then 1 plus, okay, L4, you have 6.8 times 10 to the power of negative 3. Delta T, 27. Right? So you plug in everything. Okay, the negative 3 and negative 3. Wait, yeah. Remember, this is 1 over I, yeah? So you need to flip it over. So when you flip it over, let me see. I think, yes, you should obtain a negative value. Okay, kamu sepatutnya dapat negatif. Di sini dengan nilai sini 27 times 6. Let me see what is the value. 27 times 6. It's a 162. So this one, it is equals to 1 over 10 times 10 to the power of negative 3. 1 plus 1 plus 162, I think. Yes. Times 10 to the power of negative 3. So you put it over here. Yeah, you should obtain, you should obtain a value. Let's see. Yeah, you try to calculate it, okay? You try to double check again and see how. I don't have a calculator with me right now, so I cannot check. Okay, so kamu coba lagi lah. So dia punya nilai lebih kurang begini. Masukkan, tekan keluar, and then jangan lupa flip it over. Because this is 1 over I. And what you want to calculate is I. Okay. Alright. So nanti kamu ceknya, nanti kamu cek.
Okay, madam.
Alright, so this one I'll leave it. Now let's look at example 6. So once again, if you look at example 6, you're given 2 situations. Okay, you are given 2 situations. A wire coil has a resistance of 8 ohm at temperature 80 degrees C, and a resistance of 7.2 ohm at 30 degrees C. What is the temperature coefficient of resistance? Now it's asking for alpha. Okay, questions 1 alpha. Now, if this question it doesn't give you 20 degrees C, then you yourself also have to know the initial temperature is 20 degrees C. All right, because the alpha we measure it at only one temperature, which is 20 degrees C. Kalau soalan tak bagi kamu nilai ini, kamu sendiri pun kena tahu. Yang T note Anda is 20 degrees C. Okay, so let us see. Well, usually when it comes to this type of questions, I like to form table. Okay, I like to form table. Right, where I have a case 1 right here, and then case number 2, and then their relationship. Okay, their relationship. All right, so first things I have, okay, given R, okay, I have R at temperature, so this would be my final value because it's happening at a higher temperature in this case. So my R, case 1 is 8, oops, is equals to 8, case 2 is equals to 7.2. Relationship, no, I don't know anything about them, so I will just leave it. What I do know is just R1 is not equals to R2. And then the second piece of information that we have is the final temperature T. So final temperature T1, I have 80 degrees C, and then here I have 30 degrees C. Once again, only things I know is that they are not equal. Next things, what I have next is the alpha. Okay, because now you have the same wire coil. You are using same wire coil. So this is alpha 1, this is alpha 2, but because you are looking at the same wire coil, therefore alpha 1 is equals to alpha 2, it is equals to alpha. Okay, and then one more information that I have is the R. Okay, R note, initial temperature. Initial temperature for 1, initial temperature for 2. I know that both of them, they must have the same value. They must have the same value. Why? Because first, you are looking at the same material. Second, you are looking at the same initial temperature. Therefore, R01 is equals to R02. Can you have a value that is not equal? Yes, you can. Depends on the information given. Questions might tell you, okay, now you have a 8 ohm at 80 degrees C, 7.2 ohm at 30 degrees C. All right, so you can use one as your initial, use another one as your final position. Also can, as your final value. Also can, nothing's wrong. All right, nothing's wrong. But these questions, okay, these are the information that we have. And then the next thing, okay, the next thing is, do I have the initial temperature? Well, yes, because I'm looking at the same thing. So temperature initial for 1, initial temperature for 2, they should be equal because you're looking at 20 degrees C. Okay, so both of them, T naught 1 equals to T naught 2 equals to T equals to 20 degrees C. That is what I do know right now. Okay, that is what I do know right now. Okay, so after I have all these informations, okay, I know the relationship between 1 and 2, between the variables, I can then proceed to forming equations. So equations for case 1, okay, equations for case 1, I'm going to start from equations, the general equations, R equals to R naught, bracket 1 plus alpha T minus T naught. So R final given case 1 is 8. 8 equals to R naught, bracket 1 plus alpha T final given 80 degrees C, T initial given 20 degree. So that would be my first equation. Okay, that will be my first equations. So do I have to do anything about R naught? No, I don't have to. Why? Because according to the relationship given, they are equal. So remember what I told you just now? If you have the variables that are equal before and after in case 1 and in case 2, then usually it means it can be cancelled out when you simplify the equations. Okay, dia boleh dipotong masa kamu simplify equation. Now let's look at the case number 2. Case number 2, you can obtain another set of equation, which R final is a 7.2 equals to R naught, bracket, 1 plus alpha, and then so I have bracket, final temperature given 30 degree minus 20. This would be my second equation. So if I want to cancel out the R, what should I do? I can simply use equations 1 divided by equations 2. Okay, then you should be able to cancel out the R. So if you do it, okay, if you do everything correctly, you should obtain alpha equals to 2.27 times 10 to the power of negative 3 degrees C, negative 1. Okay, degree C, negative 1. So that is the final answer. So now you try to solve it. It's actually quite a simple case, a very simple equations. Okay, it's a very simple questions. All you have to know is that you can form 2 equations, and what is the similarity between case 1 and case 2? They are similar in terms of the initial temperature and also initial resistance. Okay, and also initial resistance. So once again, 2 minutes for you to write it down, and then we will take a short break. We will continue again at 15 past 3. Okay, kita sambung lagi pada jam 3:15. So, okay, can I get an answer? I hope you guys are all right. Yeah. Okay. Before we proceed to a new subtopic. Okay, now let us look at. So 3.4, I will skip it for now. Okay, because we haven't done discussing it yet in the lecture. What I'm going to do right now is 3.5. 3.5, we have learned how to simplify the circuit in chapter 2. The idea is the same. Okay, you start from the part that is furthest away from the circuit, and then you simplify it towards the terminal. What we want to do right now is we want to see what is the constant variable in our circuit and what is the variable that is changing in our circuit. So now let us look at the resistor in series. When you connect a resistor in series, okay, we have a V here, which is a positive terminal, and this is a negative terminal. So when we connect it in series, okay, we have current I flowing, okay, according to this given diagram, we have I flowing in the clockwise direction. All right. So when I is flowing, now try to recall, okay, what is the things that give us I? The equation for I is equals to dq over dt, which is then equals to Ne over T, which tells you actually it depends on the electron, right? So if you have same amounts of charge passes through the resistor at every moment, then it means the I is constant. Okay, for example, R1, let's say if you have one charge, okay, now in the first cycle, one charge passes through R1, one passes through R2, one passes through R3, and they are all moving with the same speed, then the I will be kept constant, right? Because you're looking at I equals to dq over dt. Same amounts of charges passes through every single resistor in one cycle. Okay, dia tak mungkin R1 ada 10 coulomb, R2 got 5 coulomb, R3 suddenly got 20 coulomb. No. Why? Because they are all lying along the same path. So if they are all lying along the same path, means you will have same amounts of charge passes through them at every moment. And in that case, we say they have same I. Therefore, the characteristics of resistor in series, same current flow through each resistor, where I is equals to I1 equals to I2 equals to I3. Okay, all three of them, they have same amounts of current. Why? Because same amounts of charge flowing through it at every moment, flowing through all these resistors in every cycle. And then how about V? Okay, so again, if you look at the potentials, if you recall the things that we learned, okay, especially for group B, the things that we have seen this morning, okay, and also the things that we've learned in lecture. When it comes to V, it means the potential difference across two positions, right? The potential difference across two positions. If you look at R1, then you will have V1. If you look at R2, you will have V2. If you look at R3, you will have V3. But if you want to look at the sum of them, means that you're going to look at the potential from this point until this point. Okay, let's say you put a voltmeter right here. Then what does it mean? It means you're looking at the sum of the potential difference of these three resistors. Therefore, V total is equals to V1 plus V2 plus V3. All right. So let me go through some theory with you quickly. Okay, kita tengok sedikit theory, sedikit konsep dengan cepat. So let us see now. If you have a circuit like this, right? You have a circuit like this. I already explained it to a group B this morning, but never mind. Okay, let's just do it again as a revision. So when you have a loop, when you have a circuit, let's say you start from here. You start to look at the circuit from this point A. So from point A, if you look at this circuit, I know that my current is flowing in the anti-clockwise direction because I have a positive terminal battery, negative terminal battery right here, and I have only one battery in my circuit. So this is R1, this is R2. Okay, and then let's assume I put a voltmeter right here. This is the voltmeter. So now I start to look at the circuit from point A. Okay, my point A is here. Let's say now I have a charge. Okay, I have a charge. So this charge initially, maybe it doesn't come with any energy. When it passes through this battery, 10 volt of battery, it gains energy. And now it is moving with the potential of 10 volt. Okay, the energy is of 10 volt. So when it's reached here, your V is still equals to 10 volt. So the energy, okay, the current, the charge will keep moving. Okay, the current. Okay, the current will keep moving with 10 volt of energy. Okay, the current will keep flowing with 10 volt. It will keep flowing. So V is still equals to 10 volt. Okay, you have an I right here. And when you reach the junctions at this point, what happened is now this voltmeter will record the initial reading. Okay, this voltmeter, it will record the initial reading. And the initial reading, the potential when it is at this position is still 10 volt. So now it records 10 volt at this point. Okay, it records 10 volt at this point. And then as the current passes through R1, okay, as the current passes through R1, it experiences a potential drops. This V will drop, okay, this V will drop. Why? Because part of the energy has been used to overcome the resistance. Okay, it is being used to overcome the resistance in your resistor 1. So let's say resistor 1 comes with V1. After this 10 volt, okay, this 10 volt current, it passes through R1, it will experience a potential drop. And when it reaches this point, this I is now just moving with V. Maybe the energy is now maybe is 6 volt after it passes through R1. So it experienced a potential drop by 4 volt. Why? Because this 4 volt is being used to overcome the resistance from your R1, from your resistor 1. And as it keeps moving, okay, as it keeps moving, after it passes through R2, what happened? Now your V becomes 0. Okay, because energy is conserved in the loop, in a circuit. Once it goes back to point A, it will become 0 again. Total V in the loop is equals to 0. V rise is equals to V drops. So when it passes through the battery, it rises. Okay, it starts from 0. It passes through the battery, it rises by 10 volt. When it passes through R1, it drops to 6. And when it passes through R2, it drops to 0. Because it experienced a potential drop as it passes through the resistor, the energy is being used. Okay, it's being used to overcome the resistance. So now at this point, okay, at the end of the voltmeter, it records 0 volt. So the potential difference across these 2 points is actually the sum of V1 plus V2. Okay, let's say your V1 is 4 volt, your V2 is 6 volt. So it experiences a drop, and eventually it goes back to 0. So V total is equals to your V1 plus V2, right? If you move the voltmeter, if you change the terminal of the voltmeter, for example, now if you change it to this position, okay, you still have your battery right here. Okay, you still have your battery right here, and then this is still the same, the two same resistor, R1, R2, and then your V1 equals to 4 volt. Your V2 equals to 6 volt. Now, if you change the positions of voltmeter, okay, if you change the positions of the voltmeter, then the voltmeter right now, it will just read the potential difference across these 2 points. Where if you look at the original diagram, at this point, it records 10 volt. And after it passes through R1, it records here 6 volt. Okay, it records here as a 6 volt. Therefore, the potential, the potential difference across these 2 points, the voltmeter give you a reading that is equal to 4 volt. So it depends on where you put your voltmeter. It depends on what is the potentials, the 2 points that you want to calculate. If you look at the circuit as a whole, okay, where, for example, in this case, now I have the one in series, original diagram right here, okay, tengok balik right diagram asal. If I put my voltmeter across all 3 resistors, then my V would be equals to V1 plus V2 plus V3, right? So kalau saya alikkan dia from here to here, then my voltmeter would give me a reading V1 plus V2. That's it. Okay, that's it. So it depends on how you connect it. But if you connect them in series, you just add up the value. Okay, you just add them up, total up. So by combining these two equations, same method can be used to derive it. You look at these two equations, see which one can be used in our derivation. First one, the equation for I obviously is not suitable because it just tells you they are all equal to each other. Therefore, we are going to begin with V equals to V1 plus V2 plus V3. Okay, so once you have determined, you have decided which equations to use, okay, you sub the equation V equals to IR into our equation, our chosen equations. And then from there you derive, and eventually you will obtain R effective equals to R1 plus R2 plus R3 for resistor in series. Okay, for resistor in series. Whereas for resistor in parallel, now because you look at the diagram, all their legs, they are being joined together, they are being connected at the same junction, okay, at the same junction. So for example, now R1, both legs being combined to the same junction. R2, the leg, again, they are being joined at the same junction, okay, they are being joined at the same junction. R3, once again, is being connected to the same junction. So since they are all sharing the same junction, therefore they all have the same potential difference across them because you are measuring these junctions only. Okay, you are measuring these junctions only, and all three of them, okay, they are all using the same junction. So V equals to V1 equals to V2 equals to V3. Whereas since the charge is conserved, okay, every cycle you only have a one charge moving through one capacitor again. One resistor, okay, every cycle you only have a one charge moving through the one resistor. Then if you want to calculate the total current, you want to calculate the total charge across the three resistor, then you just add them up. So I equals to I1 plus I2 plus I3. So cara kita tengok I adalah sama dengan cara kita tengok charge di chapter 2. Sebab apa? Sebab charge, pergerakan charge yang menghasilkan current. So they are closely related. The motions of the charge and the current, they are closely related. So once again, if you look at these two equations, the first equation just tells you that they are all equal to each other. Okay, you cannot use it to derive anything. So a suitable equations, a more appropriate equation that can be used in our derivation is the equation for I, where I is equals to I1 plus I2 plus I3. So again, you're going to start to derive it from V equals to IR, rearrange it, I equals to V over R. So you sub I equals to V over R into your equations, and eventually you should obtain 1 over R effective equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, eventually you should obtain this equation. And when you look at this page, okay, when you look at a resistor in series and also resistor in parallel, there's a slight difference between resistor and capacitor. If in chapter 2, if you recall the things that you learned in chapter 2, when you have capacitor in series, okay, when you have capacitor in series, the equation is in fraction form. It is 1 over C effective equals to 1 over C1 plus 1 over C2 plus 1 over C3. Whereas if you have a capacitor in parallel, the equation is C effective equals to C1 plus C2 plus C3. So it's opposite to a resistor. Resistor in series, straight away you add them up. But when it comes to capacitor, okay, you only add them up if they are being arranged in parallel form. But in a but if you have resistor in parallel, then you use the one in a fractional form, which is 1 over R effective equals to 1 over R1 plus 1 over R2 plus 1 over R3. But when it comes to capacitor, you use the one in fractional form if they are being arranged in series. So dia terbalik. Okay, resistor dengan capacitor punya equations dia terbalik. So make sure you don't choose the wrong equations in your exam, even though equation is given. But it won't tell you which one belongs to series, which one belongs to parallel. You yourself have to know which one is for series, which one is for parallel. Okay, soalan dia equations yang diberi, dia terus bagi kamu saja. Dia tak beritahu kamu, oh kamu kena guna ini untuk series, oh kamu kena guna ini untuk parallel. No, okay, tak ada. Apa yang dia beritahu Anda cuma 4 equations ini. Kamu sendiri kena tahu yang mana satu series, yang mana satu parallel. All right, so now we are done with a series and parallel. We have learned how to derive it. We know how to derive it. We know a bit of concept on current flow in the circuit. We know how to determine the potentials. What is the potential rise and potential drop in the circuit? And then we learned how to calculate the effective resistance. Now let us move on to examples 9. Okay, example 9. Let us try example 9. So the way to solve example 9, once again, is exactly same as how you solve capacitor questions. So for the circuit in the figure above, calculate the effective resistance. Now, whenever you are given the resistance of all resistor, the first step that you should do is to simplify it. Okay, how to simplify it? Now, let us start from the resistor that is furthest away from my power supply, from my battery. In this case, we are going to start from this 4 ohm resistor. It is located at the place that is furthest away from my source. And before I simplify it, I'm going to give it a name, R1, R2, and R3. How am I going to simplify it? Let's identify the junction. Okay, the junction for this resistor. If you look at this 4 ohm resistor R1, the junction that is closer to it is this 2 point. Okay, is this 2 point. So now we have identified this 2 junction that is located closest to a 4 ohm resistor. What are we going to do? Now we want to see how many resistor is lying on this blue color path from junctions to junction. So if you look at the diagram, there are 2 resistors lying on the blue color path, meaning that these 2 resistors, R1 and R2, they are connected in series. Okay, kalau kamu ada resistor yang lying on the same path, means that they are being connected in series. So what you have to do, you just simplify them. Simplify it by using R1, okay, R12, okay, because now you want to combine R1 and R2. So R12 is equals to R1 plus R2. Well, because they are in series. So it is equals to 16 ohm, right? It is equals to 16 ohm. So after you simplify this part, okay, what you have next, the diagram will then look like this. This is your R12, and then this is your R3. Okay, this is R3. Both of them, they are being connected to a battery that is equivalent to 8 volt. So this is your V total. This would be the diagram. Next step, you simplified it furthermore. Okay, so you see, I'm doing the circle method again. I'm using the circle method again in solving example 9. So I'm going to simplify it again. Okay, let's look at the diagram. So just now I have these 2 junction in the original diagram. I've identified the 2 junction. The first path is the blue color path where you have 2 resistors on top of it. Therefore, you simplified it. The other path, you have only 1 resistor. Therefore, you don't have to do anything about it. The next step I'm going to do is I'm going to combine these 2 paths. Okay, I'm going to combine the blue color path. Okay, I'm going to combine the blue color path and the orange color path together. Okay, and the orange color path together. So I'm going to simplify it. How am I going to simplify 2 paths? How am I going to combine these 2 paths? I can combine them by using parallel method. So since they are being arranged in parallel, and after I combine them, I would have just 1 resistor. Therefore, this one I can now call it R effective. So once again, before you reach final resistor, you cannot label it as R effective. Okay, you label R effective if you have only 1 left. Kalau kamu cuma tinggal 1, then you can call it R effective. So 1 over R effective is equals to 1 over R12 plus 1 over R3. So R effective is then equals to 1.78 ohm. Okay, 1.78 ohm. So after you combine them, you will have a diagram that looks like this. This is your V still, and then this is your R effective. So based on this diagram, we know R effective is equals to 1.78 ohm, And then because R effective and V, they are being arranged in parallel. So what I have right here is V is equals to 8 volt. My VR, V across the R effective, is also equals to 8 volt because they are being arranged in parallel. So once I have V and R, I can then calculate I by using VR over R effective. Okay, by using VR over R effective. So from here, I can then obtain, you can then obtain the values for I. Okay, kamu akan dapat nilai I. So the I is, the I, let me see here, the I have right here should be 8 divided by 1.78. 8 divided by 1.78. I have approximately 4.5. Okay, 4.5. So 4.5 ampere is flowing in the whole circuit, right? 4.5 ampere is flowing in the whole circuit. And what I'm going to do next, I'm just going to reverse the circle. Okay, reverse back. So I want to see now from R effective, if I reverse back to R12 and R3, what is the things that I can calculate? What is the information that I have? So I have R12 equals to 16 ohm. And according to the diagram, R12 and R3, they are in parallel. Okay, if they are in parallel, what does it mean? It just simply means my R effective, it should be my V effective, V total is equals to V12 equals to V3. Okay, so this is the information that I have. So it is equals to 8 volt. And then once you obtain the V, you can then proceed to calculate I12 and also I3. Sebab kamu sudah ada V, sebab kamu sudah ada V, sebab kamu sudah ada V12, R12, so boleh kira I12, ada V3, ada R3, boleh kira I3. Okay, you can calculate I3. So this one, the I3 and I12, if you got it right, you should obtain R is a 8. Here, I3, let me calculate. I3 is equals to V3 divided by R3, which will then give you 4 ampere. Which then give you 4 ampere. Whereas I12, it is equals to V12 divided by R12, so you will obtain 0.5 ampere. 0.5 ampere. Does it make sense? Yes, it does. Because if you add up I3 and I12, you got I total equals to 4.5 ampere. You got it equals to 4.5 ampere. So let me change the color a bit so that you don't get confused. This is 16. 16 ohm. So kira I12 dengan V12 R12. Kira I3 dengan V3 R3. So basically you can obtain every piece of information in the diagram. You can get VIR for every single component. So last step, I'm going to reverse it back again to the original diagram. In original diagram, I know R1 and R2, they are connected in series. If they are connected in series, what is the characteristic? It tells us I12 is equals to I1 equals to I2, which is equals to 0.5 ampere. And then once you have I, you can then calculate its V, right? So I1 equals to 0.5. I2 is also equals to 0.5 ampere. From here, you can then calculate V2 and V1, sorry, here should be V1 and V2 by using I1 R1 by using I2 R2. So basically, kamu tengok, you can get all sort of information. So V1 equals to R1, I1, V2 equals to R2, I2. So you can get the value that is Okay, this is equals to 2 volt.
Two.
This is equals to 6 volt. Dapat semua maklumat. Dapat semua maklumat. Nampak tak? Kamu buat satu pusingan sahaja. From original diagram, you simplify it until you got R effective. And then from R effective, kamu patah balik, pusing balik sampai ke original diagram. Then you can get I, V, and R for every single component. So buat semua ini, baru kamu fill in the blank. Jawab questions A, questions B, and also question C. So I'll leave it to you. Okay, you answer questions A, B, and C based on what we have done here. Kamu sendiri cari nilai untuk A, untuk B, untuk C. Tapi basically idea dia sama macam kamu buat untuk capacitor. Bermula daripada circuit asal, kamu buat pusingan. Kamu pusing satu pusingan. Pusing satu pusingan. Kamu tengok apakah makluman yang kamu boleh dapat di setiap satu step. Bermula dengan R effective. Bermula dengan pengiraan R effective. Right? So now I give you 5 minutes to write it down because this one is very important. If you cannot understand this one, then you will have a huge issue in solving this type of questions in the exam. So I give you 5 minutes to write it down. If you have any questions, you may ask. Right? So remember, kita guna cara satu pusingan. Okay, kita buat satu pusingan. Okay, so now let's move on to the last questions for today's class. So far, can you understand the concept here? Boleh faham tak konsep ini, idea ini? Hello?
Kan madam?
Faham, madam.
Okay, bagus. Kena
Tak
pastikan
pusing.
Kena pastikan kamu faham. So biasanya inilah cara kita buat. Okay, inilah cara kita buat. So buat satu gitaran daripada atas sekali pusing ke bawah, and then dari bawah pusing balik. So usually it's like a 2 or 3 step. Okay, yang kamu kena reverse balik. Okay, now next example 10. This example, okay, it's being very, very nice to use. You see, they give you all diagram already. So example 10. Okay, example 10, how to solve it exactly the same as how you simplify the capacitor circuit in chapter 2. So first of all, you have to look at the terminal. Terminal is here, A and B. Now we are going to start off from the part that is furthest away from terminal, which is this 5 ohm. So again, as usual, I like to give my diagram a name. So I'm going to call this R1, I'm going to call this R2, this one R3, and then this one R4, and the last one is R5. So I'm going to start off from R1 because it's located at the part that is furthest away from my terminal. First thing I should do, I need to identify the junction that is closest to R1. So the junction that is closer to R1, obviously, is these two junctions. Okay. So once I have the junction, next step would be, I'm going to identify the path that can be taken to travel from junctions to junction. Okay, saya nak cari laluan yang boleh diguna untuk travel daripada junctions bawah ke junction atas. Alright, so from junctions to junctions, I need to identify how many possible paths that I can use. First one is this blue color path. It's going to pass through R2, and then it passes through R1, and it reaches the other junction. This is my first choice. The second choice is to pass through R3. Okay, so passes through R3, that is the green path, and then another blue color path is passes through R1 and R2. Okay, and then can you say you have another choice is by traveling through R5 and R4? No, cannot. If you do like this, means you're disconnecting this whole thing from your terminal, from your power supply. Then it's no longer valid. All right, it's no longer valid. So you need to simplify it from the part that is furthest away from the battery, but at the same time, you have to make sure you don't accidentally disconnect the circuit from the terminal. All right, from a terminal. So you have two choice that can be taken, that can be used to travel from one point. Let's say I'm going to call it point X, from point X to point Y. So I'm going to simplify path by path. Blue color path, I have two resistors, and obviously they are being connected in series. Therefore, I'm going to combine them by using a series equation. So R12 is equals to R1 plus R2, which is then equals to 5 ohm plus 5 ohm. So it is equals to 10 ohm. So now my R12 is 10 ohm. Then do I have to simplify the green color path? No, I don't have to. Why? Because I have only one resistor lying on the green color path. Okay, so green color path, I can just leave it. Blue color path, I simplified it and I obtained 10 ohm. And I cannot call it R effective because I still have a lot of resistor in the circuit. It is not the final, the last resistor yet. So I give it a name R12. So what am I going to do next? Okay, again, this is my junction. Now I have a blue color path with just one resistor, and then the green color path also with just one resistor. Meaning that I've done simplifying the path. So the next step would be combining the path. So how to combine them? Since both of them, they are being connected at the same junction, so it means these two resistors, R12 and R3, they are being connected in parallel. So I'm going to simplify it by using parallel method. So R123 is equals to 1 over R12 plus 1 over R3. So if you simplify it, you plug in the value, eventually you should obtain R123 equals to 5 ohm. Okay, R1, 2, 3 equals to 5 ohm. So after you simplified it, okay, you have just one resistor left, which is R1, 2, 3. So my next step would be identifying the junction that is closest to R1, 2, 3, which in this case, my junction would be this 2 point. Okay, the junction that is closest to R1, 2, 3 is now this green color junction. So again, I'm just going to repeat the same step. I'm going to identify the path that can be taken to travel from, for example, N to M. Okay, so my first choice would be, okay, this one, passes through R1, 2, 3, and also R4 before I reach M. My second choice would be passes through R5. So what am I going to do next? Well, if I look at the green color path, now I have 2 resistors on top of it. So I'm going to simplify it. And according to the arrangement, R1, 2, 3, and R4, they are being connected in series. So R1, 2, 3, 4 is equals to R1, 2, 3 plus R4. So R1, 2, 3, 4, it is equal to 25 ohm after I combine them. If you look at R5, now you don't have to do anything about R5. Why? Because you have just one resistor line on top of it. If you have 2 resistors, then you need to simplify it. If no, then you don't have to do anything about it. All right, so next diagram, I have orange color path here, and then I have a green color path here. If I look at my green color path, now I have only one resistor remaining in the path, along the path. And then orange color path, also one resistor. Meaning that now I've already done simplifying both paths again. And my next task would be combining the path. Okay, I'm going to combining these 2 paths. So how am I going to combine them? Well, obviously now 2 of them, they are being connected in parallel. Why? Because they are sharing the same junction. They are being connected towards the same junction, which is a N and M junction. So I'm going to simplify them. If I simplify them, then I would have only one resistor left in the circuit, which means now I can use the term R effective. Kalau saya combine 2 ini, saya akan tinggal 1 resistor. So, bermaksud sekarang kita boleh guna R effective sudah dalam kita punya pengiraan. So 1 over R effective is equals to 1 over R1, 2, 3, 4 plus 1 over R5. Right? If I got everything right, R effective is then equals to 7.14 ohm. So done. That is the final answer. And that is how you simplify it. Okay, so as you can see here, the idea, the way, the method that you use to simplify it is exactly same as the one that you use in chapter 2. So that's why I keep telling you guys, chapter 2 and chapter 3, they are very, very similar. Okay, it doesn't matter whether you're looking at the capacitor and resistor or you're looking at the circuit. They are very similar. The way you use to simplify the circuit, the way you use to change the variables and so on, the ways you use to manipulate the resistance and the capacitance, they are all very similar. So if you can understand chapter 2, then it shouldn't be an issue for you to understand chapter 3. Okay? Or if you can understand chapter 3, then you should also understand chapter 2 because they are very similar. All right? So this is the final questions for today's lesson. Let me stop the recording first.